All right, everybody, why don't we go ahead and get started? So I want to thank everybody for attending today. This is our Advanced Mixture Design of Experiments crash course. My name is Martin Besner, and I'm the president and CTO at Staties. If you'd like to contact me personally, my email is right here. It's martin@staties.com. I'm always looking for feedback, ideas. If you have any questions, I'll give you a different email at the end of this presentation that you can go ahead and use that's monitored by our entire team of consultants. So this is actually part two of a two-part mixture crash course series that we have. The first part is more introductory, more basic. It's always available on our website, and the most recent version is available on YouTube as well. So you can, if there's something that you think you might be missing today, you can go ahead and check that out. But we will do a little bit of recap as well. So if you're new, if you haven't seen the first part of this series, if you're new to mixture design of experiments, we will do about a 10-15 minute recap to hopefully get you up to speed. So just some housekeeping things. We will be muting everybody just to avoid any random noises and whatnot. If you do have any questions, you can go ahead and raise your hand, or you can go ahead and send the message. Sometimes it's kind of hard to see for me, so I do apologize if I don't get to it during the presentation. If I don't reply to your question, you can send your question here to stathelp@staties.com. This you could send it to me, but this email is actually monitored by a lot more people, so you're more likely to get a response quickly by using this email. And of course, this will be available on our website, on YouTube, and we'll also have a PDF of the slide deck available as well, probably by this afternoon. So what are we going to do today? So this is kind of a three-part presentation. The first is I'm just going to do a quick Mixture DOE recap. Okay, so for those of you that might be a little bit shaky or haven't done much work with mixtures, this should hopefully kind of get you up to speed. Then I'm going to spend the bulk of the time on advanced tips for designing mixture experiments. Now, in this presentation, I'm not really going to do any analysis of data. We're just going to focus on setting up the experiment. Tips on analysis, tutorials are available all over the place. And that's kind of one of my pet peeves, is that anytime somebody talks about design and analysis of experiments, 90% of the details are about analyzing, not about actually setting it up. So to save time, we're really going to focus on just designing the experiment. Then I'll go through some tips and tricks that I've kind of collected over my 10 plus years of working on this type of stuff on a near daily basis, and then we'll wrap up from there. So why don't we go ahead and get started with just a quick mixture DOE recap. Now, one of the very common questions I get is, do I need a mixture design? Why can't I use an RSM? Why can't I use a factorial? And I'll go through this right now. So I always like to keep the example simple because we do have people from a wide variety of industries, and if I talk too deep about a topic in pharma, it might not be very applicable or very relevant to somebody in another field. So we try to keep this as simple as possible. So let's, pizza. Suppose we're deciding what cheese we want to put on a pizza. So this might be some frozen food manufacturer that wants to put, it wants to figure out kind of what cheeses to put on their frozen pizzas. And suppose you can blend together 3 cheeses: mozzarella, provolone, and white cheddar. So in theory, you could put just one of these 3 on the pizza, but intuitively you think, well, hey, what if I blend them together? Maybe it'll taste even better. We can try various combinations of the 3 cheeses. What we're going to say is that each pizza that we cook is going to have a total of 6 ounces of cheese. Okay. My opinion, that doesn't sound like anywhere near enough, but it is what it is. Got to keep costs low. Um, but that's not going to vary. We're not going to vary, how much is the optimal amount of cheese to put on a pizza. So mozzarella on a single pizza, mozzarella can go from 0 to 6 ounces. Provolone can go from 0 to 6 ounces, and white cheddar can go from 0 to 6 ounces. Now, notice that in this case, because the total amount of cheese is fixed, okay, the amount of mozzarella plus the amount of provolone plus the amount of white cheddar has to equal 6 ounces. When you see that equal sign there on the things that you're blending together, on your factors, whatever it may be, you have basically a mixture experiment, okay? Because notice that if you put in more mozzarella, you have to put in less of the other two. Now, the responses that are measured is the appearance after baking, the taste, of course, texture. I mean, is the cheese kind of oozy or is it hard? As well as the cost. So in this situation, the components of the cheese blend cannot be set independently of one another. So for example, if you put in 2 ounces of mozzarella cheese, you can only put you can only put exactly 4 ounces of the other two cheeses total into the blend. If we didn't have this restriction, meaning all the cheeses went from 0 to 6 ounces, meaning the total amount of cheese went from 0 to 18 ounces, okay, you'd have a response surface experiment essentially. Okay, but because we're constraining it to 6 ounces, we have a mixture experiment. So this is the critical piece of evidence that you need to determine whether you have a mixture or whether you have a response surface. So a typical mixture DOE spreadsheet would look something like this. So like, use our software to generate this design. Run 1 is going to have no mozzarella. It's going to have 3 ounces of provolone and 3 ounces of white cheddar. Notice that 3 plus 3 is 6. Run 2 is going to have 4 ounces of mozzarella, 1 ounce of provolone, 1 ounce of white cheddar. So notice you add these up, you get 6. So you would prepare a pizza according to, in this case, you would prepare a pizza with no mozzarella, 3 ounces provolone, 3 ounces of white cheddar, put it in the oven, okay, and then measure the responses, and then repeat that 16 times for each cheese blend. And then notice that the sum of the three cheeses equals 6 in each run. So again, I know I've said this already 4 times, but it's really the key point to take home. So if you were doing, if you were to plot this cheese experiment on, just look at where the points are in the DOE space, you'll notice that actually, if you plot them out, all of the points lie on a triangle. So I don't actually need a three-dimensional space to represent kind of my experiment here graphically. What I could do is I can simply use this triangle here. And that's because I don't actually have 3 components that I'm varying. I only have 2 because once I set 2 of them, the third one is basically 6 minus the sum of the first 2. So what I'm going to do is I'm going to go ahead and take this triangle here and I'm going to flatten it. And I end up getting something that looks like this. So this is what a mixture design space looks like. Typically, it looks like a triangle, or we call it a simplex. Okay, so you have vertices, which represent one cheese blends. You have edges, which represent blends of 2 cheeses. You have interior points, which represent blends of all 3 cheeses. And then, of course, anytime you see a little number next to the point here, next to the run, that means we're going to be doing a replicate. So we're going to be doing it 2 times or 3 times or how many ever times the software suggests that you do it. Okay, so blending experiments should usually be set up as a mixture DOE, but not always. Okay, if you are varying the concentration or the amounts of the components, instead of something like the weight percent or volume percent or proportion, you most likely are going to have a response surface experiment. So the key, and this is the last time I'll mention this, the key to verifying whether you actually need a mixture design is to determine if any of the runs in your design plan add up to a fixed total. So in our pizza experiment, all the rows added up to 6 at the end of the day. Okay. And a lot of people ask me, well, I have a mixture, but then I'm also doing something to it. I'm boiling it at the end. I'm baking it. I'm processing it under some conditions. So it could be that, um, part of your experiment might be a mixture, like a cake formulation, okay, a cake batter formulation, but you also might have non-mixture factors as well. So for example, like the temperature that you bake the cake at, how long you put it in the oven, um, how long you stir it, and whatnot. So in that case, you have what's called a mixture process combined design. We didn't talk about those in part one of this series, but we are going to talk about it today at the end. Okay, those are very common. So there are two basic categories of mixture DOE. So when you're actually ready to build your mixture experiment, your design, you really have two options. You've got simplex-based designs, which are called which we sometimes call canned designs because they're kind of off the shelf. And the long and short is that these are used incredibly rarely in my experience. They're fairly limited. They have a very narrow range of application. On the other hand, the other option really is optimal computer generated designs. And these I use all the time. I mean, 98, 99% of the time when I'm doing a mixture, I use these optimal. So really today we're just going to talk about these optimal computer generated designs. But I will just put one slide on a simplex design so that you're familiar with it. Simplex designs are canned and straightforward. They're kind of like the two-level factorial or the central composite design of the RSM world, but they're even worse. So in order to actually use a simplex design, what you need is you need either all three components going from 0 to 100%, or all of your components going from 0 to 100%. In this picture, I have three components. In this picture, I have four components. Okay, so if I'm like making a cake batter, I mean, 100% oil or 100% egg, those are runs that are not really going to be particularly useful. Or if I have some sort of chemical reaction, putting in 0% catalyst or 100% catalyst, I mean you're probably not going to get any useful data. So it would not be applicable there. Slightly more general is all the components have the same range. So all of them have a range of 5% when you subtract the high minus the low. Again, fairly limited purpose. So they look something like this. They're very pretty, they're very even and symmetrical, but that's basically where the good stuff stops. Um, so as I basically just said on the previous slide, they're incredibly restrictive and very limited purpose. It rarely makes sense for any of those conditions to hold true, like your components going from 0 to 100%. The take-home message is this. This is kind of a tip here. Don't force, and I see this sometimes, don't force your components to have the same range so that you can use a simplex design. I just saw this a couple months ago where somebody said, well, if I expand the range of this component and I narrow the range of this, my space is going to look like that nice triangular simplex, and I can just use a simplex lattice design. Okay, chances are you're going to be cutting off good parts of your DOE space. You're going to be running an experiment. You're going to be running experiments where you shouldn't be, just so you don't have to use an optimal computer generated design. So don't do that. If you do need to use a simplex lattice design, it's here in our software. If you you open up a new design, you go to the mixture section, you can click on simplex lattice there. A better option is an optimal computer generated design, and that's what we're going to move on to right now. So here's a more realistic example of something that you might run into. Okay, I'm going to keep it to three components, because it's I can easily show pictures of it. But really, I mean, I've seen mixture designs with 22 components. I've seen 17 component designs. The same principle holds true. So suppose that component A, goes from 0 to 20%, component B goes from 0 to 50%, and component C goes from 0 to 50%. However, that's not usually enough. Let's say that there's also a multi-component constraint. So A plus B must be at least 10% of the overall formulation. Now, what that means is that I can't have A and B both be at their low. Okay. It would be really impossible to do that anyways because of the fact that C can only be 50%, so I can't have 0, 0, 50 if I'm summing up to. But the point is that I have to have some A and so I have to have some of A and B in there. However, there's also another constraint. One constraint is that the ratio of B to C. That means that the ratio of B to C must be between 1 and 1.5. So what does that mean? That means I need to have more B in the formulation than I do C, but not too much more. Like I can't go, that ratio can't be higher than 1.5. So I can't have B at 1% and C at 50% because that would be a ratio of 50. They have to be kind of within some window of each other. And finally, I have an equality constraint that A plus B plus C has to equal 100%. So in our software, the way that you would enter this is, um, and we'll do some examples later. We have a total here, 100%. You put in your individual lows and highs. You click on the Edit Constraints button, and you put in your multi-component constraints here. Okay. Now the design space looks something like this. Uh, this big triangle here is the 0 to 100% design space. This white region is the entire region that satisfies those constraints that I put on the previous slide. And then this little triangle here is kind of the smallest triangle that this white space fits into. So as you can see, if you really wanted to use a simplex here, you'd have more gray space than you do white space. I mean, the other option would be to try to cram in a simplex here, something like that, but that would be really not ideal as well. Um, so I'm just gonna, take my magnifying glass here and zoom in on that little space, and this is what I get if I sorry about my mouse here, but this is what I get if I zoom in on that region, just to make it a little bit bigger. So here's what an optimal computer-generated design looks like for this complicated design space, just to show you. If you use our software, you get something that looks like this. And I'll show you how to set this up in just a few minutes. You end up getting points along the edge. You end up getting a point kind of right in the middle. You end up getting some other interior points. You end up getting some replicates, meaning points that you should do more than once. So this is what we end up getting here. Okay. And that's what we're going to move into now. It's how do I actually use the software to set up this type of design here on the right. All right. So, so here's what we're going to do now. Now we're going to go through several advanced topics in greater detail. We're going to focus again on building the designs. Analysis is usually pretty straightforward. If you know how to analyze a response surface design or even a factorial design, there's, that gets you about most of the way there for mixtures. But there's also a ton of resources available. What we're going to start with is a deep dive on building and setting up optimal designs here. I'll also talk about some other designs, for example, space filling designs. And then we'll do a deep dive on mixture process designs. And then finally, I'll mention a couple other designs that you might run into down the road. So the general flow, here's kind of the workflow that I like to always start with. I always like to have a spreadsheet of these steps when I'm building my design and kind of go through each one, check them off. First one is choose your mixture components and set their ranges. So you basically have to know what problem you're dealing with here. You have to know what is it that you're going to be blending together and how much of each ingredient or each component am I willing to put in. I would say that 90% of the issues when somebody comes to me and says my mixture DOE didn't work, I didn't get any useful results. I'd say 90% of the time, if not more, the issue is that the mixture space was chosen incorrectly. Now, in the previous webinar, part 1 of the series, I go into this in much more detail. It's not a statistical problem, it's more of a subject matter problem, meaning you as the experimenter need to kind of come up with these ranges and these components. The next one is determine the model of interest. So eventually, after you collect your data, you're going to need to fit some statistical model that kind of describes, okay, how are the components blending together to generate my response that I'm measuring? You could fit simple models like just a straight line or a straight plane, which would be linear. You could fit quadratic, cubic, quartic. There's lots and lots of different models that could be fit. The thing is, though, is the more complicated the model you eventually want to end up with, the more runs you're going to have to do. So there's a balance. Sometimes people will say, well, I want a fifth order, sixth order model. And then they see, okay, they have to do 300 plus runs to get enough data points to support that model. We typically start with either, linear is pretty popular for just screening. But we typically like to start with either quadratic or something that's called special cubic. Those are kind of the best, in our experience, the best bang for the buck, meaning you get, 80% of the information for 20% of the runs. Okay. Most important question that I get in my entire career is how many runs do I need to do? Okay. So you need to choose the number of runs and you need to figure out what types of runs do you want to put in. Like, do you want to do some, if you have a budget of 20 runs or 25 runs, how many replicates do you want to do? How many points along the edges do you want to do? How many interior space filling points do you want to do? If you're building an optimal design, you need to set remaining build parameters, and I'll talk about those a little bit. Define the responses, meaning what is it that you're going to measure. And finally, click the continue button and it'll generate a design for you. So, and I think the best way to demo this is, best way to explain this is by using an example and doing a little software tutorial here. So once again, keeping the subject matter, the subject content fairly straightforward, we are formulating a fruit punch. And suppose that it consists of 5 possible juices: grape, watermelon, orange, apple, pineapple. Each juice blend can be independently formulated and will be tested and rated by a panel of experts. Now, they had a budget of 40 runs here. And what they wanted to do is they wanted to build an optimal design to say, hey, what exact formulations should we mix up and have our panel rate and go from there. So let's go through that workflow that I talked about and really do a deep dive on kind of all of these topics that are involved with building optimal designs. So first of all, here's what the juice scientists did. They chose their mixture components and set the ranges. So they had, grape going from 0 to 10, watermelon going from 20 to 60, orange going from 10 to 40, apple going from 10 to 20, and then pineapple going from 5 to 15 volume percent. So these were a fixed volume. The total of the 5 juices must sum to 100%. I don't remember exactly how large the samples were that they were preparing, but when you're on a percentage scale, I guess it doesn't really matter. And in theory, it shouldn't matter whether you prepare a little, 12-ounce glass of juice or a huge industrial vat of juice, because any properties of the juice should just depend on the proportion of the juices, not how much you're putting in. Okay? It's kind of like Coca-Cola, whether you drink a 12-ounce can or drink straight from the 2-liter bottle, you basically you have the same product. So determine the model of interest. Linear models can only detect linear blending properties, basically, okay, the average of 2 components. However, lots of times components will kind of quote unquote interact with one another, where you get either a synergistic effect, meaning the sum is greater than the parts, so there will be some nonlinear blending, which is what they believe to be the case here. So they chose a quadratic mixture model. Okay. Choose the number of runs in the experiment and define the properties of these runs. So the run budget was determined to be 40 runs. So here's what the experimenters decided to do in this case. This is, I think, a very smart thing, is they decided to set aside 10 of them and do 30 runs in the first pass of the experiment. So by setting aside that budget, what they're allowing for is they're allowing for any situations where maybe they screwed up and they realized, oh, you know what, we really should have tried putting in a little bit more grape juice. Or you know what, maybe we're getting kind of suspicious results after we're done optimizing. Why don't we do a couple of independent confirmation blends? So in this case, they were fortunate enough to have the budget to do 30 runs in the first pass and then kind of set aside 10. Um, then choose the number of runs in the experiment and define the properties of the runs and set the remaining build parameters. So here's what I'm going to do. I'm going to switch over to the software now, just so we can kind of go through this. So what I would do is I would go to a mixture design here. I'm going to go ahead and I'm going to go to the optimal one. Now, it turns out that if you try to set this up as a simplex lattice design, it'll complain and say that your space is not a simplex. Do you want to switch to an optimal design? But I'll spare you that. I have 5 mixture components, and they're summing up to 100 volume percent. Okay. What I can do is I can control mouse wheel to make this a little bigger, and I have a grape going from 0 to 10. I have watermelon going from 20 to 60. I have orange going from 10 to 40, apple going from 10 to 20, and I have pineapple going from 5 to 15. Yep. Easy enough? Okay. So now the software asks me, hey, what type of model do you want to fit? Well, in this case, we have this quadratic here. That's the default model here. Do I want to put in any blocks? Meaning, well, hey, I'm going to do half the experiment on one day, half the experiment on the other day, or maybe I have 2 different lots of raw material, things like that. In that type of situation, you would block. But then what I have here is I have kind of my runs. I have my required model points. That basically means that in order to fit a quadratic model to this design, I have to have at least 15 runs. That cannot be lowered. Okay, it's kind of like saying if you want to fit a straight line, you need 2 points. If you want to fit a quadratic polynomial, you need 3 unique points. I mean, that's essentially what this is here. Do you want to add any additional model points? Now, these model points in mixture designs are going to be added in a way that maximizes the precision of your design. Okay. After the model points the software kind of puts the model points where it thinks is the best. You have lack of fit points. And lack of fit points will basically take a look at, what are the biggest gaps in my space and plug them. And then finally, replicates. It'll, after all the runs are assigned, it'll choose kind of the 5 best or how many ever replicates you specify. It'll tell you which points to replicate. And then finally, if you want to force in a center point, meaning if you have a really irregularly shaped region, a lot of times what they'll do is they have a current blend. They'll use that as their center point, and then they'll kind of build their experiment around it. If you want to force in an actual center point, you can do that here. Okay. So that's what this is essentially doing here. Now, what they did is they had a run budget of 30 runs. But this is saying that I really only need 25 runs. That's my suggestion. So you have 2 options here. You can just use a 25 run design and set aside 15 runs. Or what you could do, generally what we would suggest, is to bump up the additional model points first, because that's going to give you the most precision in the actual model that you fit afterwards. So you can do 30 runs there. Okay. On the other hand, one thing you can also do is you can say, okay, I'm going to start with 25 runs, but maybe I can see if I can fit a higher order model. Maybe I can fit a special cubic model. That gives me a little bit more detail about what's going on in my mixture, which is 35 runs. So that's probably, you'd either have to shave off lack of fit points and replicates, but in general, I would just, in this type of situation, I would keep the quadratic model and I would do, say, 5 additional model points. Okay. And then finally, go ahead and set up the response here, taste 1 through 9. They used a panel, and then when you click finish, it should build the design for you here fairly quickly. And this is what we end up getting. One thing I want to add that we added to our software quite some time ago is this ability to round columns. So a lot of people don't like the fact that we've got, the software doesn't really know your precision limits on when you're measuring these components out. So one thing we can do is you can do round columns, meaning you could round off the mixture to say 1 decimal place, in which case what it'll do is it'll round off the mixture while at the same time still maintaining the equality constraint, which is 100% here. Okay, so once you have your design, you're basically ready to experiment, plug in the data, and do the analysis in the way that you would ordinarily do it. Okay. So tips and tricks for run size. So the software defaults here are fairly safe. So if you just go ahead and spam click continue throughout, you'll get, I think, what's a fairly safe design, meaning it's, uh, not too big, not too small. If you have no strong feelings towards a particular design size, the defaults, I think, are a good place to start. If you need to cut runs, we suggest lowering the replicates and the lack of fit points. We recommend a minimum of 3 for each as the very minimum. If you cannot afford any, just set them to 0. I mean, if you don't have the budget for them, you don't have the budget. You could also consider lowering the model order. So instead of fitting a quadratic model, fit a linear model. But I mean, I'd rather almost just take a gamble on fitting the higher order model rather than fitting a lower order one, having a lack of fit test tell you it's not enough, and then not having any budget to continue on. If you have lots of extra runs, meaning you have a pretty generous run budget, consider increasing the model order before adding extra model points, replicates, or lack of fit points. In this case, we tried to go to special cubic and it gave us 35 runs, which was a little high. And then one thing is that unfortunately we don't have the time to go through this in great detail here, but use the FDS to guide you in sizing your design. An FDS score of 80% is recommended. Now this, we have a webinar just on this topic, so I highly recommend you check that out if you get the chance. This is really the, when you're fitting factorial designs, you look at power. We generally don't look at power for mixture designs. We look at FDS, fraction of design space, which is a measure of the precision, meaning how precise is your model going to be? How stable is it going to be, expected to be? All right, our next topic that I'm just going to briefly talk about is space filling designs. Now, this is another category of mixture designs. This is fairly new in Statis 360. It's only been, a few years. And what they aim to do is they aim to quote unquote fill a design space. So evenly distribute points without leaving any large empty spaces in between the points. So this is not a perfect example. This is just a little illustration here. This design here clearly looks more space filling than this design here, because here you've got, huge cluster of points and you've got this, massive empty space here. Massive empty space here. So space filling designs, it should be a design that you're aware of, and they can be used in a wide variety of cases. I've actually used these more and more over the past few years. So first of all, they're especially useful in if you're doing a computer or a simulation experiment, where you're using a simulator to generate your response rather than an actual lab experiment. Space filling design is perfect because you don't want replicates. You want as many unique different runs as possible. A space filling design will do that for you. It'll give you the maximum information in your case. Space filling designs can also be used in exploratory studies or range finding experiments where you have a lot of uncertainty about your design space and you just want to test as many unique design points as possible to kind of figure out where you should even be experimenting. So in this stage, you're not looking for where is my response good, where is my response not good. You're looking for where can I even get measurable data? So space filling designs will give you, more unique points than other optimal designs, and therefore will give you more information about your new experimental design space. Finally, if you expect like a sharp peak in your response, meaning, your response might be flat, then you might have a sharp peak, or you might have a sharp valley, a space filling design has a higher chance of actually catching that. So here's just an example. If I were to, let's say design for a quadratic model, I might get runs here, here, and here. In which case, if I fit to this run here, I fit to this run, and I fit to this run, I basically get a straight line. Okay. But if I have a space filling design, and I try to spread my runs out, okay, I have a higher chance of my model actually being able to catch this behavior here. Okay, and those are just three cases that I can fit on this slide. There are lots of other ones as well. And here's just a little demo comparing space filling designs to optimal designs. So once again, three components. A goes between zero point 0.5 and 1, B goes between 0 and 0.4, C goes between 0 and 0.5. So this is on the proportion scale here. And what I'm going to do is I'm just going to show you, using our software, what a space filling design looks like, what a modified I optimal design looks like, and what an I optimal design looks like. So this modified one is kind of the default one that I had showed you. So these are the three options. This is meant to just be a little graphic here to show you really, how space filling designs will differ from an I-optimal design for a quadratic model. You could see that an I-optimal design puts, most of the points along the edges and maybe some points in the middle. And that's fair because if you're fitting for a quadratic model, most of that behavior that's going to be modeled is at the edges of the design space here. Okay. Um, so you can see here what's going on. This is meant to just be a little bit of an illustration here. So really the moral of the story is that um, if you are fitting a quadratic model, you are actually going to get slightly better properties with this I-optimal design. But if you're looking for, hey, I want to kind of hedge my bets, I kind of want to test as many points in the design space as possible, a space filling design is going to be useful. Okay, and now we're going to go on to our last category of designs, which are mixture process designs. Okay, and these are Um, I don't know what the exact percentage is, but these are probably pretty close to being just as common as a mixture only experiment. So as I mentioned about 20 minutes ago, you might have a formulation that you're working on, but you're also processing it under different conditions. So like if you have a cake batter, you could be baking it at several different temperatures. Now, historically, long time ago, what would happen is they would have basically two separate departments. What would happen is you'd have a formulation team, and what they would do is they would take kind of the processing factors and set them to the middle setting, middle temperature, middle time, middle whatever, and they would then formulate. They try to figure out, okay, where is my optimal formulation going to be? What are the component, what are the components? What are the amounts? And then the formulation would be sent to basically the engineers, the chemical engineers, and they try to figure out, okay, how do we, ideally process it? How can we scale it up? And so on. So basically, it was two separate experiments that were done. Now, there is a better way to do this type of experiment, which is why we have this category of designs now, which is a mixture process design. So one disadvantage of the two-stage approach that I mentioned in the previous slide is that the fact that the ideal mixture, it's often going to depend on where the process parameters are. So really you have kind of this interaction between the formulation and the process parameters. So a formulation that, is ideal at high temperatures might do awful at lower temperatures and so on. So kind of based on where your process factors are, that's the that's going to affect what the formulation is and vice versa. Okay. So a mixture process design models the effects of the mixture, it models the effects of the process parameters and the interaction between the two, which kind of gives you a complete picture of what's going on. And these are almost always built as computer generated optimal designs. So final demo that we'll go ahead and go through. And again, just keeping it simple, three components of a cake batter formulation were being experimented on. And then what they did is, once they had a cake batter, they baked it at a pre-specified temperature in the oven. So the three components that they were varying was sugar, going from 10 to 50 grams, vanilla, going from 1 to 1.5 grams, and raspberry juice, going from 2 to 3 grams. Now, these three components need to sum to 50 grams, although each cake actually weighs 200 grams. So what they're doing is they're holding things like flour fixed, and they're varying kind of the sweeteners, things that make the cake taste sweet. But in addition to working on the cake batter here, they were also tweaking the temperature. It went from 350 to 400 degrees. Okay. And it could be that, based on some properties of sugar and whatnot, that, if you're baking at a higher temperature, you might want to put in less sugar and more raspberry juice or whatever. But you can't find that out if you do this as a two-stage experiment. With a combined design, you can do that. Okay, so what I'm going to go ahead and do is just show you how to set this up so that you're aware. So I'm going to close this design here. I'm going to go to New Design. I'm going to go to Optimal Design here under the Custom one. And I have 3 mixture components and I have 1 numeric factor. Now my mixture component A was sugar, which was 10 to 50 grams. Vanilla, which went from 1 to 1.5. And then I had raspberry juice, which went from 2 to 3. And then my total is 50 grams. And it's software is complaining that, I can't have 50 grams of sugar in the formulation if I have to have at least 1 gram of vanilla and 2 grams of raspberry juice in there. So what it's going to do is it'll typically adjust the upper bounds first. Okay. And if I go back, I can kind of see what the new constraints look like here. Okay, and then finally I have the oven temperature, which is 350 to 400. If I click next, this goes through the same process that I talked about a few minutes ago here. Just for the sake of time, since we're running out of time, I'm going to go ahead and just show you how to build this design. And then you're going to get something that looks like this. You're going to get a mixture here, a 3-component mixture, but then you're also going to get the process factor here. So this is going to say, make a cake batter with 46.7 grams of sugar, 1.2 grams of vanilla, and 2.0 grams of raspberry juice. Bake it at 377 degrees. Okay, this is one, of course, maybe I might round. So like I might round the oven temperature to make it a whole number. Maybe I want to round my mixture as well to, let's say, how many grams can I measure out to? I'm going to just measure out to 1 gram here. And I end up getting something that looks like this. If these oven temperatures don't work, you're going to go ahead and have to manually adjust them, or you should have made them a discrete factor at the beginning. Like if you only want to go in increments of 5 or increments of 10, you would set this design up by using a discrete factor. But anyways, this gets you your experimental layout here, your plan. So just some other designs to be aware of. One is a double mixture design. It's kind of like a combined design, except you have 2 separate mixtures that are part of the experiment. So like a cake batter and a frosting formulation. The 2 mixtures may depend on one another. Up to this point, every time I've been showing an experiment, we've always assumed that everything's done independently. We're making, 1 cake batter and then baking it, and then making another cake batter and then baking it. If you're in a situation where you have to put 6 cakes in the oven at the same time because it's just more feasible, or if you have to make big batches of batter and then split them up, you're going to want to look at split plot or restricted randomization designs. And then finally, there's also a mixture of mixtures designs, which is if you have, 3 different mixtures that you're ultimately blending into a final mixture. So finally, some other tips and tricks. So this is kind of the practical part here that we're going to wrap up with. The first, these 5 come from the first part of this webinar series. So if you want a really deep dive on each of these topics, you can go back to the first part. So the first one is, don't use factorial designs. A lot of times people, what they'll try to do is try to shoehorn in a factorial design into something that's obviously a mixture. It doesn't work in every case. And even when it does work, it doesn't work well. So I generally recommend just investing the time to learn about mixtures. Okay. On a similar note, one thing that I often hear is people will say, well, you know what? I'm going to convert to ratios. so then I can use a factorial or response surface design, and I don't have to use a mixture design. And once again, this is not a great idea. Um, I think it's kind of a headache to constantly be converting between ratios and volume percent, and you don't get great designs because of the fact that you're working with ratios. So unless a ratio really is scientific, meaning you have a scientific basis or a subject matter basis to use ratios, that's fine, but I don't like using them as a workaround for mixtures. Spend most of your time choosing your components and ranges because huge percent of whether you succeed or fail is going to depend on what components you chose and where you're experimenting. Experiment iteratively, especially if you have new problems. If you have a fairly decent run budget, you don't need to use the entire run budget in your first experiment. You can spread out the run. You can spread out the runs. You can do some of them at the beginning, analyze the data, see where you're at. If you like the results, you can keep doing what you're doing. But if it turns out that hey, you should have added a component, or you should have added more of one component or less of another component, having some runs in the bank will allow you to keep your original experiment, tack on a few extra runs, and keep experimenting without having to start over. And then finally, master building optimal designs. I mean, even with this tutorial here that I did, it's only 45 minutes, but you should have at least an idea, hopefully, of where to start. It doesn't take all that long. And then finally, here are more tips and tricks. This is for the advanced practitioner. So if possible, analyze mixture process experiments as a single experiment rather than doing them separately. And I talked about this before. Use KCV models for mixture process designs whenever possible to save runs. Those are the default, so there's not really much you have to do there. Fully randomize a mixture experiment. Okay, so when you're going from one run to the other, we assume that you're formulating independently and you're resetting the process factors. Now, if that's not possible, that's fine, but make sure you set it up as a split plot design. When in doubt, start small and build up. Don't deplete your run budget in one pass if possible. And finally, use the FDS plots to right size your design. Power is generally not recommended. So just to cap off here, Mixture DOE, it's a very popular tool that unfortunately I think doesn't get much attention, especially in the statistical field. I mean, it's basically, even in the DOE world, mixtures get very little attention. Design Expert and Statis 360 software contains all the latest and greatest tools that you'll need. Once again, I guess earlier I said it was going to be the last time I say it, but I'll say it one more time. The key to recognizing a mixture experiment is determining if there is an equality constraint. There may also be process parameters in your mixture experiment. So if you enjoyed this presentation and found it useful, I mean, we have, check out our YouTube channel. We have tons of formulation mixture DOE videos there free. We've got lots of case studies on our website, tutorials in the software, and we also do have a live workshop. We have a 4-day distance learning workshop where we go through these topics with the software with an instructor. So we basically take this 45-minute presentation and spread it out over 4 days so that you get to go through everything, as well as learning how to do it in the software. So I want to thank everybody once again for attending. Hopefully you got something out of this. Again, I'm very happy to get any feedback here directly. If you have any questions, please email stathelp@staties.com. That'll get you quicker answers than if you email me directly. So thank you once again. We hope that you found this useful, and wish you good luck in all of your experiments going forward.